All right. Hey, everyone. Welcome to our talk, Building a Graph-Based Infrastructure. Quick introductions. My name is Ryan Turinsky, lead software developer at OCLC. Been there for about 13 years now. Father of two girls. Two interesting facts about me. Unfortunately, tragically cursed with being a Dallas Cowboys fan, and I'm a huge Marvel fan.
My name is Hakeem Shittu. I'm a principal software engineer at OCLC. I've been there for just about 7 years now. About the most interesting thing about me is a woodworking hobby that I've been, at for a couple of decades now, trying to get better each time. We're here to talk really about how to set up a graph-based infrastructure and a little bit about where we're from. OCLC is located in Dublin, Ohio. Ryan and I, myself, is introduced, work there. We're a nonprofit organization which manages data for multiple libraries, and we provide their sort of shared technology services for these organizations. And one of the main things that we support and we control is this data set, this massive data set known as WorldCat. And WorldCat data set contains about 600 million bibliographic records, which is metadata about books, movies, lots of items that you have in libraries. We also have within our data set 3.2 billion article records and also 1.7 billion holdings, authority records, library metadata. These are all items that are growing, and these are all items that are managed and maintained by a group of catalogers, data specialists over time. So these are just constantly curated and constantly updated data within the organization.
So a little bit more background about how OCLC got into doing knowledge graph. So libraries are always seeking opportunities to make scholarly materials and their other collections more discoverable on the web. They also want to expand opportunities to connect their collections to other relevant collections. Enter us. So we got awarded a grant from the Andrew W. Mellon Foundation to develop a shared entity management infrastructure that will support linked data management initiatives underway in the library and scholarly communications community. With the creation of this centralized infrastructure, it will provide linked data entities that are discoverable, reliable, and sustainable, and will provide a critical foundation for libraries working to achieve these objectives. So this was a 2-year project, started in 2019, December, went through the pandemic, finished up just at the beginning of this year, and really close to being done, right? Maybe. There should be some press releases coming out here at the end of this month, hopefully, or in June, to talk about more about that. And so that's why you're getting this two-headed dragon attack for this, because Hakeem got to do a lot of the back-end stuff, the infrastructure. My team was involved with doing the front end and our APIs that we'll go into. All right. So one of the building blocks for a knowledge graph, is data. You need a lot of data to build this knowledge graph. Guess what? OCLC has tons and tons of data, as Hakeem just mentioned. But we need linked data. So what is linked data? So taking a look here, this is worldcat.org. So scenario, you're going out, you're looking for anything, books, and you find yourself upon this result. Also a huge Iron Man fan, so this is a good one. And so you're presented with a bunch of information about this book or graphic novel. Author, publisher, editions, summaries, what have you, and even more information that you don't see. The cool thing about this is that there's links off to other things. So if you want to find a different edition or format, or if you wanted to know more about the subject, or if you wanted to find more about the author, well, you can click on the link and you can go find more about this author. And it takes you to a different document, and you can see, okay, here's what Peter David also wrote. Now this is really cool for us humans, right? We're discovering more, we're doing great, we're getting more information, things are linking very nicely. However, this isn't great for a computer, right? Computers don't understand that while this is a picture, right, they don't know that this is the cover of the book I'm looking at. They don't know that Peter David is the author. They don't know it's linked to somewhere else. They don't know anything about these other editions or these subjects, right? So what we do as software developers is we spend a lot of time deconstructing this data from these websites and turning it to something that's a little bit more readable for these computers. We turn it into properties and values, right? Title, creator, publisher, date published, and everything else. These are all properties and values. However, this data is still living on an island by itself, right? We don't know what the book's Iron Man here, his relationship is to the rest of the world. We don't know Peter David's relationship to the rest of the world. It's just there by itself. So much like websites, right? If you start adding links to this data, you can actually find out more. Machines can start reading this stuff. So you can see here, taking a look at up in the upper left corner here, there's links off to Peter David or Marvel. And so a machine can start understanding that, hey, this book right here has a relationship to Peter David, and that relationship is through the creator property. Or this book has a relationship to Marvel through the publisher property. And what we can do with each of those pieces of information is express it in this format. This is a statement built with the subject, predicate, and object. Right? This is the basic building blocks of a sentence. It's readable by humans, but still, machines don't quite understand it. Right? Computers like to be very specific. They want to know which specific Iron Man I am talking about. Right? It could be the book, it could be a podcast, it could be a movie for all we know. It doesn't understand what this creator thing is in there in the middle, the terminology, and it doesn't know what Peter David is. It could be Peter David, the author, it could be a composer, it could be a Peter David in this room. No, that didn't land. Okay. Oh, wait, is there a Peter David in here? Did you write this? No, okay. Or, for example, in the movie No Way Home, when they were trying to beat the bad guys here, and they were all confused and like, hey, we can't do this. So they started calling themselves Peter 1, Peter 2, Peter 3. You need to be specific about what you're talking about, right? So there's this concept called a URL. It's a unique identifier. And with these URLs, we can distinguish between different things or know that one thing from one data set is the same as another in a different data set. And so by adding URLs, you can get very specific about what you're talking about. So this is what linked data looks like to a computer. So a computer can start on the subject node. It can follow the creator link all the way to this object node. And the good thing about this is that one of the things about these is that these URLs have to be resolvable, right? I can't just take this link and me as a human go onto a browser, put that into a web browser, and have it 404. It has to return something. It has to resolve. So this, overall, is called RDF. And this is the general method of describing data by defining relationships between data objects. And RDF stands for Resource Description Framework. And so there are multiple formats you can express RDF in. So you can express it in N triples, which is pretty much that statement concept, just URLs there at the top. I know it might be a little hard to read. Oh, that's not too bad. There's JSON LD, which is the linked data format of JSON. This is the compact version of it, so it's a little bit more readable to humans. And if you didn't have this little context there at the top there, then that would be the expanded version, and so you'd see a lot more links for the field names. And there's also N quads, which is the extension of N triples. It's just an extra spot where you can provide more context to what you're talking about. And there are other formats too. There's Turtle, N3, and RDF XML, but these were the main ones that we worked with. And so to recap what linked data is, Tim Berners-Lee came out with these 4 design principles for linked data. 1, use URIs as name for things, and we went over that, right? You gotta be specific. Use HTTP URIs so that people can look up those names, right? I wanna know exactly what Peter David I'm talking about. And that goes into number 3 there. When someone looks up a URI, provide useful information using the standards, hence RDF. And that include links to other URIs, right? This is linked data. Just include links so they can discover more things. And now, our next building block that we want to talk about is this one part in the middle, which is the predicate, right? We want to talk about these properties. And Hakeem will talk about that.
Okay. So, to talk about the predicates, we have to talk about what an ontology is and building out an ontology. And so the idea really of the ontology is you have these classes. The goal of the ontology is you have semantic data and you're trying to link how these data relate to each other. So within that, you have to define what are the classes that make sense for the data that I hold. Also, for all the classes that make sense, what are the attributes that each of these classes have, and what are the relationships that exist between the classes. That vocabulary that you define, this entire corpus of these are my classes, these are my relationships, and these are the attributes, and these are also how the relationships, how they relate to each other. That set becomes your ontology. That is what is known within your object, within your graph in there. There are several examples of this that exist. Schema.org has some of the ontologies provided. Doubling Core is another one. There are several of these that exist. Basically, it is within the space of what you're trying to describe. What is the language? What is the fields? And what are these attributes that make sense? In a way, you can look at this as a generalized data model. This is what I have for my data, and this is what I know about that. Now, there are multiple approaches that exist when you need to create an ontology or define an ontology for what you're working on. But one of the approaches we looked at in this is to start from something that exists. You can build your, if I take a person model, for instance, I can choose to, have first name, last name, and use F name and L name for first name, last name, and that might work within my organization. But in a lot of these instances, we want to see how else are other people defining persons? How are they defining these classes, these known entities? And so we often start with an existing ontology and then say, what do they have that we need, and we could use that, and we extend from that to actually match our own very specific use case. If there are certain things this ontology might have that we don't need, in a lot of cases we can remove that. So that's sort of the approach we followed. We started from a base, and then we built upon that. Because the data we're trying to provide, the data we're trying to make available to people is data that exists within bibliographic data, how these objects, these library objects, these library artifacts, if you will, link to each other, who created them, when it got created, who was the publisher, and that type of information. So we started with a schema-based ontology, and then we adapted it from there to suit our needs. So in this case, for what the ontology is, you have the classes. An example of this, for instance, will be books, would be a class within that, authors, publishers, location, subjects. And as you look into this diagram, you would actually begin to see the relationship that exists within each of these, right? So certainly, books are written by authors, and the same work is published by publishers. So that gives you an idea of how these items can relate to each other, and also makes it possible to find this item. So that's the next slide about that. So books are created by authors, books are published by publishers. Now, this is something that's clearly known to humans. If I have this data, if I have someone going behind the machine to search for this, they can make that connection themselves. What we're trying to do, however, is to go beyond humans being able to find this, to have a machine find their information in a fast and efficient way. So this brings us to what this data looks like if you actually apply it into a graph, right? And the kind of questions that this becomes possible for us to ask becomes something like, list all the works that Peter David created and was published by Marvel. Right, so that becomes something that's a lot easier to search for from a computer. Give me the names of all the creators whose works were also published by Marvel, right? In a lot of cases, if you're trying to do this, you have a data set, right? The size may differ, but you have an existing data set in which you're trying to make available. And in almost all cases, your data set is often, accessible in an RDBMS table, set of tables somewhere in a relational database system. So you can access your data today using SQL, right? And one of the questions that I got asked a little bit about this will be, what was the value of taking this data from the SQL context, something I can find in SQL, and then moving it to this semantic context? What do I get from this investment of time and effort? And the idea behind that is this: you're making it possible by increasing the relationships between the data sets that you have. You're making it possible to answer things in a faster way without having a human search element in it, right? So it becomes the building blocks of being able to have, your system go in and ask, very similar to the questions that are listed here, generated from machines, and machines being able to answer that. I think one of the examples that we have a little bit later in the slide is the Google Knowledge Card. If I go and ask information about a specific individual, give me information about Peter David, I can get information about him, and then also information related to Peter David based on the graph built around him. So this takes us to knowledge graphs, and there are multiple forms of graphs that can be built with semantic data, but the very specific one that we're going to talk about, the very specific one that we've built, is a knowledge graph, because again, for our very specific use case, we have a lot of data about a lot of things. And we've built an extensive search infrastructure around it to make it possible for you to go in and find it, right? You go into a library, you want to find information, you're very likely hitting one of our systems to make that available. And we're trying to go a little bit beyond that and turn this discrete data values that we have into knowledge, right? So trying to find the relationships beyond just here is a table that has data. We're trying to match up these relationships, and the knowledge graph is the way to provide that. So of all the different graphs that exist, the knowledge graph for our use case is what makes the most sense. And so the idea is it provides this relationship between real world entities and also the information that relates between them. So this data set that we have, we're trying to link them together in a way that makes it possible for users to have access to them. There's a quote here which is things, not strings. And that really ties to, in a non-linked world, a lot of what you're doing is you're doing text searches. And there's value in text searches, certainly, but a lot of times if you're looking for something, the specificity of what you're trying to get is really based on a person making a search, tweaking that search based on the result they get, and then doing a second search to get maybe a finer-grained result. A knowledge graph removes that need for that, or I should say, significantly limits the need for that. So in this case, your knowledge graph is your data that you have, extracted, linked, and then layered over the ontology you have defined. And once you have that, you now have multiple data access formats to access your data. So very similar to for your RDBMS, you would access that in SQL. In a knowledge graph, you would access that in one of these languages, Sparkle, Gremlin, OpenCipher. We'll talk a little bit about these three specific ones, about why we chose some of the infrastructure that we did to do that. But several examples of this exist today, that you can look for. You have Wikidata, has something similar. You have Google Knowledge Graph, you have Facebook Open Graph. All of these are different graph data formats that are available. I should say different knowledge graphs that are available. So the idea is, if I'm going to build this knowledge graph, what are the pieces of items that I need? And a lot of this really centers around the graph database. So for a lot of what we're talking about for a graph infrastructure, spoiler, the graph database is sort of at the core of it. It's in the middle of it. And there is a lot of things that were built around it to provide data into that graph database, and also to provide data coming out of that graph database to make it accessible for people to see. So that's the first main option that you have. Now, if I want to do this, I also have two options really when it comes to graph databases, or I should say two main models that I have to consider. You have a labeled property graph and you have an RDF graph. Now, for our specific use case, we had to support RDF graphs, but also there are additional internal uses that we had. So we ended up with a scenario where we actually have two graph instances. We have both a labeled property graph and an RDF graph. And in this case, it makes it possible to use these three languages that are sort of listed beside that. And what I've done is just, what we've done into a small degree listed. OpenCipher can only work with property graphs, Gremlin also with property graphs, and then Sparkle endpoints, which is part of what we had to provide, makes use of RDF data. What this diagram tries to showcase a little bit is the same data that exists in your relational tables, or in fact, if you have your large NoSQL data stores also, this is a way of moving that from, or this is an example of moving that from a relational model to a graph model. And typically what you will see in this relational model is all your tables are linked using primary keys and foreign keys. And this is really easy for a human to navigate through, right? So we have, you pull up an entity relationship diagram, you look at the different tables that you're trying to pull information from, and then you sort of walk through the primary key from one table to the foreign key of the other table, and makes it possible for you to write a SQL to do that. Imagine someone sitting across the world that needs to get access to that same information without access to the same, table relationship diagram that you have. How would, we're trying to reduce the path between the initial source and the data that they're trying to get to. And so in the graph form, instead of going from a person table to a person-friend table, which will be the link table, and then to a friend table, which has a list of your friends, you're able to go directly and say, you have this person knows these other individuals directly. So I can use a predicate such as, who does Peter David know, and get information immediately instead of trying to navigate through the nuances of SQL. The graph database that we use, and I think when I get to this aspect, for the infrastructure we're going to talk about, there is a lot of options that exist, right, in this space, and it grows every day. And specifically, we chose Neptune for the graph database. A big part of that is we're an AWS environment, so we have a lot of things within AWS. Certainly, Neptune being an AWS Graph as a Service was one of the major options, one of the major benefits, but also specifically because it supported both LPG and RDF versions of Neptune. Now, I should make a note that when you do that, you cannot use the same instance for both the RDF and LPG instances. So what we have is 2 instances of Neptune. We have the LPG instance, which we do a lot of our internal data milling. We do a lot of view generations. We'll talk about that also in one of the succeeding slides. And then, of course, we also have an RDF instance because that's one of the endpoints that we had to provide to individual. It helps that part of what Neptune supports is up to 100 billion nodes and edges. We don't have that yet, but certainly, when you're building this type of infrastructure, you want to make sure that you're using something where you have the capacity for growth, right? So there's this elasticity of growth as we add more data sets as we proceed. Also, because it supports both LPG and RDF, or more specifically, it actually has support for all these three query languages that we use, and we actually use these quite extensively. The final deciding factor of Neptune was sort of this part of the documentation is being able to support 100,000 concurrent queries. Now, we've not tested that capacity yet. I think our current model is about 150 million entities and growing. We certainly have the data set to grow this into the billions of records, but we're currently at 150 million records and growing, but we wanted to make sure that the choice of infrastructure could support this future where people will do up to a certain amount of queries per second. Okay. So, as we begin to talk a little bit about the infrastructure aspect of this, what we try to do is to identify sort of a 6-step approach for this, or really just breaking this down to about 6 different steps of what we took to do this. And the big first step of this is identification of your use cases. So you can't build a knowledge graph for everything, right? You have to define what do I care about? What am I trying to showcase? What data do I have that I'm trying to make available to people to see, right? And that helps you define your vocabulary and create your ontology. So within the OCLC space, we have a team that was very helpful and instrumental in creating and designing this ontology. I'm trying to look out to see very specific faces, but there's a bright light up there, so I can't see anyone, but I know they're out there, and they did a lot of hard work in trying to make this, define this and make it available for usage. Now, the other thing that's really great and important about graph models and ontological models is these can grow over time. You can add to things as you know it. You're not blocked in once you have this model. And once you have, if I were to add a new attribute for a person, or a new attribute for book, or in fact, a new type of bibliographic material that did not exist today, or in fact, let's make NFTs into bibliographic material. Well, we don't really have to do a lot to do that. We can build onto what exists. You don't have to remill your data. You don't have to make a lot of changes to it. You are adding new claims, new knowledge into what exists into your graph, and immediately becomes available. Immediately you can define how this relates to any of the data that you have existing, and your application can make this appropriate adaptation to support them and to start to query them. So once you've done this, once you have this ontology in place, then the very next thing is to pick out your tech stack. What will my tech look like? And to a large degree, this depends on factors within what environment you're using, how quickly you're trying to get this done, the size of your pocketbook. You can define any tech stack, but you still have to pay for it, right? So we had to look through these choices and then make choices that made sense for our organization, the size of data that we had, and we'll provide some of the choices we made in the later slides. Now, it's important and crucial to know that these are, just the choices we made. A lot of what is available can be done with maybe other choices. So maybe in cases where we chose Kinesis, you can choose Kafka, you can choose RabbitMQ, something else that is similar within the environment. Also based on what the size of your data is. If you have a smaller data set, then that might be an option for you to make a different choice. If you're maybe using a different cloud provider, GCP, Azure, any of those, then you may have slightly different options that are available to you, but still the concept of this remains the same. Now, once you have defined your tech stack, then you begin sort of the laborious process of getting your data into your graph, right? So I know what my ontology looks like, I know what the fields or the relationships are. So here are all my nodes, here are what my edges will look like. These are all the pieces of technology that I'm going to use, the language stack, all of that. And then, I have to take my data out of the existing data source that I have this in, and then convert that into my data set. You typically have to do this in two sets. One of that is the initial entry of this data that you have, and then once you have that, now you have to manage your update flows. As we'll look through in some of the later slides, our updates come from multiple sources. So not only do we have to create this initial data set of several billion records that will go into it, but we also have to manage the maintenance and updates as people make changes over time. The new books get created. We discover that maybe the names of authors were a little bit incorrect and they get updated in different languages, so all of that information still has to flow into our graph. Now, in our specific use case, we needed multiple ways to access this data. So there is the transactional data flow that we have that goes into the graph, but we also have, for different UI use cases, you have groups that actually needed to do some archival reporting on this data. Now, in that case, it didn't make a lot of sense to have them do this directly from Neptune. We also had the need for people to do fast access to data, being able to use things that maybe search engines are great for, right? So I want synonyms. So I want to find, I want to search for Peter, but I want to use a synonym of his name. I want to, Pete or something like that, right? So we had a couple of these use cases to be able to do that, and that involves step number 4, which is materialize your views. We will define, as your data goes into this large data set, into your large graph data set, how do you push the data into the views to make it accessible for people to actually make multiple uses from. Once you're at that point, you're really close to the end-ish, right? Ish in this case is you build an API over that to make sure people that access it, that's where your security layer comes in. Certain approaches that you want people to use to access. Are they going to send you raw Sparkle and then you process that? How are you going to simplify some of these access use cases? And then you have your UI to build and to make it available for people to come in, do this search, and find that information that is needed and available. So this is a flow of that process that I've defined. Certainly the ontology process is not a part of this, but this is that data flow that exists. And I'm going to go through this a little bit quickly, but as we proceed, if there is any questions about it, there's a chance we'll come back to this slide because this contains a lot of the data flow and the distillation process, right? So in our case, we have multiple sources where data come from. We have the WorldCat table that we talked about. OCLC also maintains these VI of data sources where we pull people from, and then you also have fast data source. And these are also constantly updated, constantly maintained. And we took this information in. I'm going to go back and forth in my slides here just to tie it back into the decanting process. And we have the idea of what is called a fact extractor, which is where your data is stored in an initial form. In some cases, it might be in a table. In some cases, it might just be in large block files. And these block files have very specific formats. You have to look at your data format and say, what am I extracting out of this data format, of this data, to match up with what fits into my ontology. So if I have a name, and my ontology says I have to have given name and I guess preferred name and given name, then I have to decant that into, I have to extract those facts out of my data source, the appropriate data source, and then I push that into a process which we call the enricher process. The enricher process makes it possible that if I pull this information from VF, for instance, I pull a person, I can go to other sources and say, what does the world know about this person? What are some additional information that other ontologies may be aware of about this person that makes sense for my specific knowledge graph to pull in? So we do that enrichment process. And we push this into a messaging middleware. Now, in this case, we're talking about the next slide, very specific ones that we use. But the idea for this is to allow things to be processed parallelly at scale, right? So we're using kinesis for this, and the very next set of items becomes our linker process, pulls information out of kinesis, in which case it is in quad form. Effectively, we have subject, we have the subject, predicate, object, and then this additional context, which in some cases you need to use a context in a lot of cases. If I have 6 Peter Davids, I need to know which specific Peter David I'm talking about, and so you can use some context information to link this across to maybe some of the other data sets you have from our bibliographic system. We go through a process of duplicate detection and duplicate removal, right? If I have 6 Peter Davids, there may really be 5 unique Peter David, and one of them is just a Peter David that had been created from another one of these data sources, and we have a process that tries to do this identification within a certain level of confidence, and then says you have this in your graph, or you have this already, this Peter David already, and so we're not going to load the second one. Once you can make it through this pipeline process, then that's the very next step, is loading this into our Neptune graph database. Now, to a larger degree, for a lot of users, this might be the final step that's necessary. In our case specifically, however, we needed to also take the same data and then make it available in a set of views. And a big reason for this sort of becomes the specific use cases that these views need, right? There is one of these, which is Snowflake, trying to not look into that light a little bit. There's one of these, which is Snowflake, and that is what we're using for sort of the large-scale query and archival, reporting flows that exist. We have a view of these entities in an internal data format that is made available in Aurora. What makes that, why we make use of that is you do a search, you pull a person. I don't want to go in and pull a lot of the interconnected facts about that person in real time. I want to pull access for that object directly from where I have pre-composed that view. And so we have that stored in Aurora. Certainly we have an RDF instance of Neptune that takes the LPG data, reifies it, and makes it available in Neptune in RDF format. And then finally we have Elasticsearch, which makes it possible for you to still do this. There are still applications that have a need for just the text search model, right? So creating a graph doesn't automatically mean that every single application within your own enterprise will go into a graph model. So for these applications that still need to make use of text search and still want to pull this data in a text format, then we have the Elasticsearch instance that actually looks at the same data set, pulls that information in, and then adds all the good search items, the synonyms, and all of these items to it. The very next step of that, we made our API access available, and from the API access, the UI layer becomes something that pulls data from that API access. In this, we certainly have the ability to create elements in the graph, not just from any of the sources that we pull information into, but also from from the UI. So our UI gives the user the ability of saying, well, I have a Peter David that just wrote a new screenplay for the next Marvel movie, and not the existing Peter David, so I want to add that person into the model. We have that facility in doing that through our UI, and the UI base uses the same API layer to actually provide this information that goes back into a graph and then gets milled into our views. This is the specific stack that we have used, and what I've done is I've underlined the specific ones that we have, and in each of these layers I've actually provided what are a list of available options that are there. So you need processing engines, and that is one of the big things here. You need to do a lot of processing, especially as the number of sources you pull data from grow and multiply, and the number of updates to this source grow and multiply. And also, within organizations that have large data sizes, it's not unusual for batch processing to occur that then does an update for a few 100 million records at the same time. So you need a processing pipeline that has this elasticity of being able to absorb the large number of updates that may come at a certain time, and then certain period of times you may have drips of updates coming in. So in our case, we chose Flink as that processing engine to do that work. Flink pairs very well with Kinesis, which is, again, part of the AWS offering. And within that messaging pipeline, in a lot of cases, you need something where as your data comes in, your data can flow into this messaging middleware. Specifically, that's where the elasticity of processing comes in. So at certain times, you have a lot of messages in, and you use your messaging pipeline as a queuing mechanism for that. We had a couple of options, several options of graph databases, and so some of these are listed out here. And previous slides talked about the reason why we chose Neptune specifically, and from there we had 4 data access containers, very specific use cases, which as we maybe go through different slides or questions arise, we can talk more about these use cases. And then finally, for our user access layer, we have Spring Boot, which is what the API is based around, and the UI is based on React and Next.js. One of the things that I probably did not include very specifically on this is the language. So we are heavily Java. This is a Java stack primarily as the base language in which work is in there, and there is some Scala in there too, also.
Yeah, just to go off script for a second, Hakeem, how many entities did you say that we loaded?
150 million.
150 million,
Yeah.
all right. And Wikidata only has 97 million entities, so I'm just going to throw that out there. Make of that what you will.
Yeah.
So anyways, okay, so what Hakeem had just mentioned, we built an API. It's your standard RESTful API. We have the creates, reads, what have you. One of the things that we did is have a Sparkle endpoint, so we can have users query our graph directly. And this is just an example of one of those queries. So you can kind of see here, this is the query language that we use for it. It was just pretty much just asking, hey, please select me everything that has a label of Iron Man and in English. And you get all these different links, and you can, again, take those links, throw them out in your web browser, or have the machine read them, resolve to something. And then our read API, or read endpoint, this is the JSON LD format of the entity that we showed off earlier, the Iron Man graphic novel. So again, going back to those linked data design principles of if I resolve to something, it better be RDF, and this is our JSON LD version of that one. And then the other format for our read endpoint is what we call our entity JSON, and this is actually what feeds into our UI here. So it's not too bad to see. Okay. So yeah, this is what I was able to smuggle out some screenshots of our UI. Not yet, again, released, but hopefully no one finds out. So we have different information on here. And one of the cool things with Next.js, right? Next.js gives you the ability to do server-side rendering or client-side rendering because we're using React. So what we had to do here, looking at our entity JSON here, you get basic information about the entity that you want. Like you got the description, aka the summary, different aliases, and what we call the label or the title or the person name, right? But we have links, right? We want to show off that there's relationships to this. And they're all just IDs. So if you can kind of see the squint to your eyes, there's entity ID up there. That's our distinct ID for each of our entities. And so we get that in our entity JSON. So we actually have to go out and get those. And so instead of showing off the ID here in the related persons, we're actually showing off their name. So what we do is that we render server side just to get very basic information out there about this entity. And then on the client side, we just go ahead and make another call and say, hey, give me every single related label entity so I can display it pretty on the page for you. And then jumping out there back to Peter David. So one of the other things that we had to do too is include external sources about them. So Peter David, you can kind of see here, if I want to find out if this is the Peter David I'm looking for specifically as a human, I can go take a look at some of these external sources. I can go find out, hey, look at IMDb. He has an IMDb ID. I'm going to go jump out there and see if this is the exact Peter David I'm talking about.
Okay. So anytime you're doing this, one of the things we decide we added into this is you run into some issues which may be unique to the graph creation process. And so the idea was adding this slide just to talk a little bit about some of these issues and then how we worked on and how we sort of resolved these issues in there. The first part of this is the correctness of claims, right? So everyone's been to Wikipedia. Everyone's seen, some issues that arise when claims are made. Now, in this case, you can have a closed graph certainly, and it's only available to employees and people to make these changes. In which case, you may not have to worry about that. So this may not be pertinent to every single, graph use case. But in our case, we're making this available to a very large number of users to make changes to. And so there is a possibility where a claim gets into the graph that may not be, that we're trying to decide or determine the correctness of that claim. And so we're trying to we solve this using the idea of provenance, right? So with each claim, there is a source that make that claim, so you can always sort of tie it back. But more importantly than the source of that claim, we also have sources which are trusted sources. So if a claim were to come true of a certain source about a person, maybe it came from VIAF, because that is also a data set that we maintain, then we might decide that that is a more trusted claim than if this was added as a third party, and there might be some lack of clarity or lack of confirmation around that claim, right? So that's the idea. So that's the resolution approach we took, is being able to provide trusted sources for these claims. With an open graph, a lot of times you also have to allow competing claims into the graph. So a very good example of this might be having an individual that has, several different birthdays, because there's not really good consensus about what birthday that individual has. Now, I'm going to go back a couple of slides to how we resolved this, or the approach we took to this is in the top corner right there, there's this blue score that gives you a quality score of that individual, this entity, I should say. And what that does is what makes it available for us to see is how much does this entity, the data about this entity, adhere to the constraints within the ontology, right? So within the ontology, it indicates that a person, expectedly, would have one date of birth. And if a person has none or more than one, then it begins to affect the quality of of the scoring for that entity. Because if this was a non-controversial fact or well-known fact, then there will be one verified date of birth for that individual. So still, we keep those information into the graph. These informations are available within the graph, but it still makes it. But when you go and view that person, we make it clear to you, or we make it available for users to see that there might be there's a certain adherence of this individual to the quality score, or I should say it has a reduced quality level based on some of the issues around how it adheres to the ontology. Preventing duplicate entities, because this exists a lot. There are several Peter Davids in the world, there are several Adam Smiths in the world, and if someone were to add a Peter David, how do I say, well, we already have 5 and you can't have a 6th Peter David, right? So, this is a rather tricky use case to do, because and the way this will have to be implemented will differ very significantly for different environments based on, what you're trying to accomplish, what your rule sets is, maybe what some of your source of data is. In our use case specifically, we use an ML tool from Rosette, so they have an RNI tool which sort of forms the backdrop of our duplicate identification, and it uses several different fields from this individual that is being added to make a determination that do we have this existent person in the graph, and if that's the case, this is who that duplicate is. It is not unusual, for instance, specifically when it comes to persons, to have people have some people are known by alternate names, or in fact pen names, and so within the graph we're trying to make sure that all of that information is grouped together around the same physical entity or around the same entity. So this tool is how we were able to achieve that, to make sure that anytime you had a new addition into the graph, we could try to identify if we've seen that person before, and if so, this is who that individual might be. Other issues that matter, especially if you have a graph, the data set size that we have is issues of scale, right? So you have to be worried about the query performance getting degraded with the number of relationships you draw across, your entities, with the number of entities you have in the graph itself. Like we indicated, we have 150 million at this stage of the entity, but we also have data sets that number in the billions, which means that our graph size is going to grow rapidly. And if you have the core entities in the billions, and then you're going to have, of course, the relationships extrapolating from that, also makes the size of a graph grow. Now, anytime individuals go in and use a graph, regardless of what size it is, we are very, people are used to sub-second performance, right? And so the concern was, as the graph size grows, what could we do to make sure that we are not impacting the ability for people to pull information out of the system? And one of the ideas we sort of came about this was to identify, well, what are the specific competing use cases that people need to, and is every query really a graph query, right? And that is where the idea of the materialized views came from. So if there is processing that users need to do, if I need to do maybe a large-scale processing and give me the names of all persons that exist in your data set that have, that were alive within this large era, this 100-year era, I will get a few million records, and it will take some time to pull that full couple million records out. We did not want a use case like that to be a graph search use case, right? We don't want someone going in and then pulling that information out. If you have those use cases, we do have support for that, and that's where we have our applications that have those needs go into a materialized view to pull that information out. Excuse me. The other part, which comes up quite a bit, it is a process of linking, right? So I have this work, and I'm trying to link this work to a Peter David, and I have several Peter Davids. How do I know this is the right Peter David? There's a lot in here about how we resolve this, but this is one of the reasons why we actually ended up with an LPG instance, because internally we're able to keep metadata about each of these individuals, and that metadata is what we use to do the linking across, and that, with clarity or just with certainty that this work was created by this individual with this very specific VIAF ID, and that VIAF ID is the same VIAF ID that has the same as relationship with Peter David, and so, by extension, Peter David actually created that work. So there is, certainly for graphs, this is a core aspect that people worry about, and people will try to make sure they get correctly. There are all concerns that exist in this case. What happens if you have the works of two different Peter Davids merged together? That begin to have an impact on your graph. So, this is certainly something that we spent a decent amount of time on, and like I said, our approach is using additional metadata to, do the stitching across. There are lots of additional considerations and concerns if you're trying to do this, and one of them that we've sort of highlighted here is the idea of bidirectional linking. So an example for this would be if you have a person and you're defining a sibling for the person, right? So now I have Peter David, and Peter David has a sibling. Do I go in and make an update in Peter David to reflect that sibling, and also go into the siblings graph to reflect that sibling? Well, what if Peter David is one of 10 siblings? Do I now have to make 9 additional updates to each of his siblings? So that's the first item that comes in with these bidirectional linkings. The second concern there is, just like you have a parent and a child, right? So Peter David has a parent that might be in our data set, and also has a child that might be in our data set. If I were to do a search, now I need to have a way of saying this is an inverse relationship. So Peter David's child, searching for the parent of Peter David's child, should give me Peter David, right? So those are the kind of concerns that exist when you're building your graph, and possibly one way to look at that is, if this isn't a core part of your use case, then that's really part of what the ontology tries to determine is, if users are not coming to my graph to look for maybe the parent and child relationship between these individuals, then I may not have to do bidirectional linking for that specific source, right? So this last one, the answer is it depends. It depends very heavily on what your knowledge graph is trying to do and how you're trying to surface that information to the world. Do you have anything to add? All right. So some references from some of the materials that we used, and we'll take questions.
If you could repeat the question or rephrase the question so that the audience and the other theaters can hear. So this goes back to, I think, that flow slide you had. So when you use the create API, does that data go through the extractor and enricher process that normal sources would go through?
Actually, no. So the question is, when we use a create API, does the data flow all the way back into the extraction process? In our case, if you're doing a create, and with this diagram, the actual version of it has a lot of lines going in a lot of different cases. So we sort of try to create an abbreviated version without showing a lot of the relationships, as clearly as what it would be. But no, in our case, this only goes as far back as the linker process, because now I've created this individual, and that becomes a source, and I need to now make sure that it is not a duplicate entity, right? And how does this individual link and load to other entities that I have within the graph? So it doesn't go all the way back to the start, certainly. It actually ends up in this process.
Okay. Another question was, can you dive into why you chose Neptune over Neo4j?
Specifically in our case, we needed something that would do both. So the question is, why do we choose Neptune over Neo4j? Our use case specifically needed, so within the library community, an RDF, a Sparkle endpoint was something that was core, an item that was needed. I don't believe Neo4j has that as an endpoint, so that very immediately limited that as an option. Now, since we're using really two instances of Neptune, we could use LPG Neptune here, and then something else for, we could use Neo4j, I should say, for the first instance here, and then Neptune for the RDF instance, which would work. But, again, as with all of these items, if you're already using Neptune, and Neptune provides support for both items you need, there wasn't really any need for us to go in and, double up on the cost and then, the components within the stack.
Should also be mentioned that for the first year of this 3-year project, we did use BlazeGraph, containerized versions of BlazeGraph. And I think we just kind of said, we don't want to do this, let's have AWS manage it. Let's have this idea of kind of like Aurora, right? Where you have a writer endpoint and a whole bunch of read endpoints with read replicas inside of there. So it made it really nice to let AWS handle that for us.
Correct, yeah, and a very good part of that is, yes, managed services also was, I think I might have included in one of the slides, but yes, when some of these items as a managed service sometimes becomes a bit of a tipping point, especially if you're trying to do a lot at, a lot in a very compressed time window.
Okay, we've got, actually, we've got two more, one more just came in. So, how is temporal versioning of data handled in a graph database?
Question, how is temporal versioning of data handled in a graph database? The answer is in an interesting way. So we have the idea of qualifiers, and qualifiers so with each statement, or I should say within an LPG graph, you're able to hang onto that LPG relationship some attributes within that. And what we've done is we're able to hang off, across this relationship, attributes, for instance, a temporal attribute or time range. So an example of that will be, I have a person attended an institution, right? So Peter David attended OSU. I don't know that for a fact, but let's make that rumor up. So Peter David attended OSU, and that's a fact, right? But he's still not in OSU right now, so we added a qualifier, so a metadata to that relationship that says there is a temporal period between this year and this year is where he actually attended OSU. So that's the way we've actually handled that for several things that have that type of temporal relationship.
All right. The last question we have is OpenCipher widely used in your system/user base?
So the question is OpenCipher widely used in our system or in our user base? No, our user base is very heavily Sparkle, so that's why we have that as an endpoint. Internally, we're actually using a lot more Gremlin, right? But the syntax form of OpenCipher is something that helps us make the choice. There is a SQL-like nature to that, which the hope is, as we end up with endpoints that expose OpenCipher, it becomes a little bit easier or becomes something else that our user base would be able to query and get information out of in there. But right now, our externally exposed endpoint is the Sparkle endpoint. Internal heavy usage, we're using the Gremlin, but OpenCipher is something that we're very interested in exploring just because of what we think it can do and the simplified nature of it.
That's all we have in Slack right now.
Oh.
Thank you, guys.
Thank you.